quick segment here, just to clarify something in the textbook about apparent weight. So we've been saying that the weight of an object is mass times the acceleration due to gravity g, but technically weight is just the name that we're giving the force of gravity. So we know it's the gravitational constant times the mass of the object times the mass of Earth or whatever other planet we're on divided by basically, if we're on the surface of the Earth, we're talking about the radius of the Earth. If we are at some other distance above the surface, then we're talking about some distance, some separation between the object and the center of mass of the Earth. So this weight is a function of separation distance, of altitude, in other words, above the surface. But that's a subject for another segment. The thing I'm really interested in is how does that? So okay, we have ourselves a spring scale. So we hang a mass on here, and it's calibrated so that when we hang a mass of the object, we end up saying that the reading is something, that there's a tension up, a tension or a spring force or something, and the weight down. And it's in equilibrium, so we know the tension is equal to the weight, and so we've measured the weight of the object. But that we've never taken into account before the fact that the Earth is rotating. This trick works because we're able to say that the sum of the forces is zero because equilibrium. But if a thing is rotating, then it definitely has an acceleration, and it's not actually in equilibrium, which is something of an issue. So let's clarify what's going on here. The best way to do that is to show you a diagram. At the North or the South Pole, the angular velocity of an object hung from a spring is zero because it's not actually, it's on the axis of rotation. I mean, I guess maybe there's an omega, but there's no v, right? Because v is omega r and the radius, right? If we're on the axis of rotation, the tangential velocity is zero. But an object hung from a scale at any other point between the two poles, any latitude between 0 and 90, there's going to be some circular motion associated with the fact that the Earth is rotating. So this point here, an object at this point, is describing a circle here at some latitude, I don't know, 30 degrees north or something, which means it's describing a circle, which means that there is some radial acceleration. Let's talk about an experiment done at the equator. The math is a little bit nicer to us there. If the issue is that the upward force from the scale, the one that gets us our actual reading, and the downward weight of the object, the actual weight of the object, according to the masses and the distance that the mass is from the center of the Earth, those forces have to add not to zero because it's not actually in equilibrium. It has to add 2mv squared over r, because this is an object that, if we're on the equator, is actually, so, you know, there's the Earth, and we're rotating this way, and the center of the Earth is down here. So this distance is r, and in order to be on the surface of the Earth rotating, it needs to be, yeah, mv squared over r. I don't know what speed this is. I guess it's the speed of the Earth's rotation. So it has something to do with the circumference of the Earth and the 24 hours that it takes to rotate. But whatever it is, it's fine. The two forces in question, we know that this has to be radially inward, so I'm going to make that negative in this coordinate system. Alpha is positive. The force from the scale is up. The actual weight of the object is down, equals negative m0 b squared over r. So the apparent weight, the reading from that scale, the force that it needs to use to hold us up, we add, it's the weight of the object less whatever the centripetal job is. So if we factor out m, the weight here is, okay, that's like the gravitation on average, gravitational strength on Earth, minus v squared over r. We have to make this magnitude correction to the strength, to the apparent weight and the apparent acceleration due to gravity, because we're actually moving in a circle. At some other point, let's say here, somewhere at some latitude that isn't 0 and isn't 90, there's actually a directional problem too. The acceleration associated with the circular motion doesn't point towards the center, it points towards the axis. It points radially inward of the circle that is all at the same latitude. So that that radial acceleration is perpendicular to the axis about which we're rotating, not in the same direction as the force due to the gravitational attraction between the Earth's mass and the actual rotating mass. So there's a directional problem there too. We need this to be a vector thing, that the direction of the weight radially inward and the direction of the radial acceleration associated with moving in a circle, we'll just say a radial, a centripetal, I suppose, and the direction of the apparent weight of an object is going to be different from the actual towards the center direction because of this centripetal correction. It doesn't amount to much, maybe 1/10 of a degree or so, but it's something that we need to consider, especially if we're going to try to do, Henry Cavendish style experiments to figure out the strength of gravity. Okay, next segment.